Most people think space is complicated. It's not. They just learned it the wrong way. In this series, you will learn space the way engineers actually use it. And today we fix one idea that almost everyone gets wrong. Orbit. Okay. Right now, above your head, a 400-ton space station is falling towards Earth, but it never crashes. Why? Most people think satellites stay in space because there is no gravity. That is completely wrong. In fact, gravity at the ISS altitude is almost 90% as strong as it is right here on Earth. So think about this. If gravity is pulling it down, why doesn't it fall? Let's forget space for a second. Let's come back to Earth. If I throw a ball, it falls. If I throw it harder, it goes further, but it still falls. Now imagine that, throwing it really fast, faster than anything you have ever seen, and as it falls, the Earth curves away beneath it. So what happens now? The ball is still falling, but it never reaches the ground. That is orbit. A satellite is not floating. It is falling constantly, but it has also sideways motion, and that sideways motion is incredibly fast. Two things are happening at once. Gravity is pulling the satellite down and velocity is carrying it forward. Just like the cannonball in Newton's cannonball experiment. The satellite that we are launching will have a tangential acceleration that taking it forward, and at the same time it will also experience a downward acceleration called centripetal acceleration due to the gravity. As the combined effect of these two acceleration, the satellite will experience a net acceleration, or simply the effect of gravity will change the direction of the velocity experienced by the satellite, and the result, it curves down trajectory and the satellite as it moves forward. As the combined effect of these two acceleration, satellite will experience a net acceleration, or simply effect of gravity will change the direction of velocity experienced by the satellite, and the result, it curves down the trajectory of satellite as it moves forward. So as we said, satellite is not flying, it is constantly falling towards Earth and missing it. How is this happening? How much initial velocity should we need to give to place the satellite in an orbit? To understand this, we need to know briefly about the centripetal acceleration. Centripetal acceleration is what keeps things turning instead of going straight. It is same acceleration experienced by a ball tied at the end of a rotating string. From the equation of centripetal acceleration, gravitational potential, we can find the From the equation of centripetal acceleration and gravitational potential, we can find the minimum velocity of an object to stay in orbit around a planet instead of falling it down. V orbit will be equal to square root of gm by r. You don't need to memorize the equation, but here what it tells us: too slow and you fall back to Earth, too fast and you escape it completely. Exactly right, you stay in that orbit. Every satellite you have ever launched depends on hitting that number. This is not just theory, this is exactly how space agencies place satellites today. Every GPS signal you have ever used, every weather forecast that warned you of rain, every satellite image you have ever seen, all of it depends on this. And the engineers at ISRO, NASA, European Space Agency, they use the same logic every single time they launch. Now here is that interesting part. You are going to try this yourself. In the next session, now here is the interesting part. You are going to try this yourself in the next session. You will control velocity and try to build your own orbit. You will fail at first, everyone does it. But when it clicks, you stop memorizing space and start understanding it. Welcome to Launchpad. Let's put something in space. ഇതിലും ബെറ്റർ നേരത്തെ പറഞ്ഞല്ലായിരുന്നു അതിലെ അല്ലേ? നേരത്തെ പറഞ്ഞ പക്ഷേ കുഴപ്പമില്ലല്ലോ.